This is B. Naresh, working as assistant professor in ECE department. And today's topic is principal operation of BJT. So here, the BJT means bipolar junction transistor. So in the last sessions, we discussed that one semiconductor device that is nothing but a PN junction diode. If you observe in a PN junction diode, it contains two materials here. One is a P-type material, another one is your N-type material here. And when we biasing the PN junction diode under the forward bias and reverse bias, it allows the conduction only the forward bias condition here. And in that PN junction diode, the conduction takes place with respect to only the majority charge carriers. But coming to this bipolar junction transistor, and the conduction depends upon both the charge carriers here. So that is either majority charge carriers or a minority charge carriers here. That is the reason the name it is called as the bipolar here. Then to construct this bipolar junction transistor, again we need to use the two different types of the materials here. One is a P-type material, another one is your N-type material here. And by using this P-type and N-type material, we need to form a bipolar junction transistor. And based on the construction of the bipolar junction transistor, the conduction depends upon both the charge carriers, that is majority as well as your minority charge carrier. So this is one of the advantage of BJT is compared with your PN junction diode. But in the case of PN junction diode, the conduction takes place only with respect to your majority charge carriers. But here, the conduction depends upon majority as well as your minority charge carriers. What are the majority and minority? And if we consider the materials like a P-type material and N-type material, and based on the doping concentrations, and a P-type contains the majority charge carriers are holes and the minority charge carriers in a P-type is electrons. And similarly, if you consider the N-type material, in an N-type material, the majority charge carriers are electrons and the minority charge carriers are holes here. Now here, we need to form a two PN junctions diodes are connected back to back, then it looks like a bipolar junction transistor. And why we are designing this bipolar junction transistor? So most of the cases, if you want to perform a amplification or to improve the signal strength at the output stage, then we are going to use this bipolar junction transistor here. But if you observe the PN junction diode, we discuss some of the applications like the PN junction diode simply acts as your switch, or it can be used in a rectification process and some clipping and clamping operations here. Similarly, here also the bipolar junction transistor. Most of the cases, the bipolar junction can be used in this amplifiers and oscillator circuits as well as the switch in a case of digital circuits. So amplification means, your amplifier means to improve the signal strength or to increase the signal strength at the output state. So oscillators means we need to generate some amount of frequency or oscillation, and that can be generated done by using this bipolar junction transistor. So another one, the simple application of this bipolar junction transistor is switch. Simply it acts as a conducting state as well as the non-conducting state. So based on the conducting and non-conducting states, we can represent that the bipolar junction transistor acts as a switch here. So how it produced levels, so off-state levels as well as your on-state levels here. So that we'll discuss in the part of applications of the bipolar junction transistor here. Now coming to you, So what is actually, so the name, the BJT indication is, the abbreviation of this BJT means bipolar junction transistor here. So here the transistor is divided, means it can be separated, means transfer plus resistor, and that transfer resistor is defined as your transistor, means that the signals how we are transferring the information. So in this case, by using this transistor, we are transferring the low resistance to the high resistance devices. Means at the input side, we need to create a low resistance input circuit, and output side, we need to make that a high resistance circuit. So while to design any bipolar junction transistor or to define the operation of BJT, we need to satisfy it always transfers the low resistance input circuit to the high resistance output circuit. So that is the reason the transistor defined as a transfer resistor. So hence we are transferring the low resistance input to the high resistance to the circuit at the output side. We need to define. So means that here we are going to use two PN junctions are connected back to back. But so in that PN junction, we are having the materials, P-type material as well as your N-type materials here. But we are not using the complete PN junction diode here, but we are using the two different PN junctions material, P-type material and your N-type material. And those two PN materials are formed as one junction, and those two junctions are connected back to back. Then it forms the a bipolar junction transistor. From that, here, so if we consider any bipolar junction transistor or a transistor, most of the cases in this transistor, it contains three terminals. Suppose if you are observing the PN junction diode, and this is the symbolic representation of the PN diode. If we observe this PN diode, it contains only the two electrodes. One electrode is represented as your anode. Another electrode is represented as your cathode. Similarly, based on the construction of your bipolar junction transistor, most of the cases, the transistor contains only the three terminals. That is, one is emitter, another one is the base, another one is your collector. So these are the three terminals for a BJT: emitter, base, and collector. So similarly with PN diode. So PN diode contains only the two electrodes, anode and your cathode. But here, these electrodes are represented with terminals. One is a emitter terminal, one is a base terminal, another one is your collector terminal here. Now we'll see what is the functioning of each and every terminal. What is the functioning of emitter, what is the functioning of the base, and what is the functioning of collector. And in this case, if you consider again in a PN junction diode, so in a PN junction diode, both the materials P-type and N-type materials are equally doped here. But here coming to construct this bipolar junction transistor, so here these are individual, means different doping concentrations we are employed to construct the bipolar junction transistor. Means that emitter doping levels are different, base doping levels are different, and the collector doping levels are different. But if you compare with the PN diode, this is the PN diode. In a PN diode, P-type material and N-type materials are doping with the same. But coming to this bipolar junction diode, so doping levels are different in each and every terminal. Emitter is some doping levels are different, base is different, and collector is different. So if you observe, and based on these three terminal representation, so emitter is heavily doped material here. So here emitter is heavily doped. So why? Because of that, why this emitter is heavily doped means So based on the doping concentration, emitter is always emits the charge carriers to allow the conduction in a bipolar junction transistor. So here the emitter is acts as a source to a bipolar junction transistor. That is the reason. So if the doping levels are increases, what happens? Your charge carriers are also increases. So if the charge carriers are increases, then what happens? The conduction rate is also increased. So that is the reason. Here the emitter is heavily doped and it always emits the charge carriers. And in the case here, emitter is either based on the material. So if you have taken that either P-type material or N-type material, well, here if you consider the N-type material, the majority charge carriers are electrons. So here it emits the electrons towards the another material, but here that is nothing but your base. And coming to your the base is very lightly doped. So here the base is very lightly doped and the region of this base is a very thin. The region of the base is very thin. Suppose if I consider this is the construction, let us take, and this is suppose if I consider this is the emitter, E means emitter, and this is the base, and this is collector. Just can observe this one. Emitter is heavily doped. So emitter is a heavily doped, and the base is lightly doped. But the region of base is very thin, means the width of the base is very thin here. Why we are making this width of the base is a very thin means, if you observe this construction, the emitter is always emits the charge carriers to the opposite terminal, another terminal. So here the collector function is to the collector is always collect the charge carriers from the emitter here. Suppose if the base region is a very large, what happens here? Most of the charge carriers are combined with the base, and some of the none of the charge carriers are not reached to the collector. That is the reason. To reach the charge carriers, whatever the charge carriers are emitted from the emitter, that should be reached to the collector. Hence, we need to place the region of the base should be very thin here. So when we are making the thin region of the base, most of the charge carrier means whatever the charge carriers are injected or emitted from the emitter terminal, all the charge carriers are trying to reach to the collector to produce the conduction across the bipolar junction transistor. But thus all the charge carriers are traveling through the base region here. So that is the reason. Here I represented this one. So here base is lightly doped and the region is a very thin and it passes the most of the emitter injected electrons onto the collector. So now on representation of these two, so we discussed up to this point. Emitter is always emits the charge carriers. All those charge carriers are traveling towards the collector through the base. That is the reason. The collector functioning is always it collects the charge carrier. But what is the doping levels? So here emitter is heavily doped and the base is a lightly doped. But the collector is intermediate between this emitter doping levels and basing doping levels. That is the reason. The doping level of the collector is represented as your moderately doped. Means always the doping levels are lies between base and emitter doping levels. So from these three representations, we identified that emitter is heavily doped, base is lightly doped. You remember this one. So in a BJT, doping levels are not constant. So each term have some different doping levels. And here the C means collector. So here the collector is moderately doped. So then, and coming to the regions, means the width of the terminals, emitter and a base and a collector. And here, and we observe here, the base region is very thin, but collector is very large region. The region of the collector is very large region, and emitter region is moderately region here. But doping levels are highly doped material. Emitter is highly doped material, but the region is moderately. B base is a very lightly doped, and the region is a very thin. Collector is a moderately doped, but it means that is lies between the doping levels of base and your emitter. But the region or the width of the collector is very high. So hence, I'm representing this symbolically. So let us take this is emitter width region. Base is very lightly doped, and this is the collector. So you can observe this one. This is the region of the collector, and this is the region of the emitter, and this is the region of base. So means base is always very thin region, collector is very large region, and emitter is moderately region. These are the regions or widths of your terminals, and these are the doping levels of your terminals, emitter as well as the base and the collector. So from this, what happened? The collector is always collect the charge carriers, means whatever the charge carriers are emitted from the emitter, and those charge carriers are traveling through the base and it is reached to the your collector. So why? Because of the why the base is a likely to me. Again, the region is a very thin, means we need to pass all the charge carriers from the emitter to the your collector. So So that is the reason we find this one here. Based on this, all this construction, the collector is the largest of the three regions here. Then, and coming to you, this bipolar junction transistor has contains two junctions here. So, so based on these two junctions, it forms the three terminals, that is emitter, base, and a collector. Then, how we are going to form these two junctions? So these are the standard junctions in a transistor. So one is always the junction is a form between emitter and a base. One junction is a form between emitter and a base. Another is formed between the base and a collector. So means depends upon the BJT. The BJT has two junctions. Those two junctions are represented as one is emitter base junction, another one is collector base junction. So one junction is formed between emitter and a base. One junction is formed between base and your collector. So, and based on this representation, here I'm going to show that how to construct this one, means so we need to take two PN junctions here. So here, the two PN junctions are connected back to back. Then it forms one transistor. And based on the formation of the transistor, it creates the three terminals. And those three terminals are namely, it is called as emitter, base, and collector. Where E means emitter, B means base, and this is called as the C means your collector. And we know that this is which type of material? This is the P type material, and this is N. Again, this is N, and this side is your P. These two N materials are connected, shorted, hence it forms a one N type material. And based on this representation, this type of the construction is called as PNP transistor. This type of the construction is called as the PNP transistor. So based on the construction, so here the transistor is classified as two types of the transistors here. One is PNP transistor, another one is your NPN transistor. But whatever the transistor, it contains only the three terminals, emitter, base, as well as your collector. Now, if you see in another way of construction, and again here also we are in the two PN junctions are connected back to back. But based on this construction, you can see observe you what happened. This is N-type material and this is the P-type material. Again, this is P-type and this is your N-type. So here these two P-type materials are shorted, hence it forms the one P-type material here. And based on this representation, this type of the transistor is called as your NPN transistor. So, based on the utilization of the junctions or PN materials and based on the construction of your two PN junctions here, then it is classified as the two types of the transistors, PNP transistor and your NPN transistor. So, whenever the two joints are interconnected and that interconnecting point is called as the base. That interconnecting point is called as your base. And one again, apart from that, it contains the two opposite ends. One end should be defined with the emitter. One end should be defined with the emitter. One end should be defined with the collector. Similarly here also, if you take in the PNP, the two end materials are shorted and that terminal is called as your base. And opposite two ends are defined with emitter as well as your collector. So this is the construction of a bipolar junction transistor. Based on this construction, and we identified that the BJT is classified as your two types of transistors, PNP transistor and your NPN transistor. But in the case of PNP transistor and emitter contains P-type material, hence the majority charge carriers here the emitter is holes. And if we consider the NPN transistor and the emitter side, which type of material we formed your N-type material, hence in this case the majority charge carriers are electrons here. Now, this is some symbolic representation here, NPN and PNP transistor, and this is represented as the base, and here this is emitter and the collector. Similarly, this is base. You remember this one, what is the material is there. Based on that material, we need to satisfy the definition of the So then it contains, this is the emitter and a collector here. So in this case, we need to identify that, we need to know, remember this one, which type of material is used for emitter side and a base side as well as your collector side. Why? Because of that. So we need to satisfy the definition of the transistor. So what is the meaning of transistor? The transistor means it transfers low resistance inputs, low resistance to the high resistance device here. So hence input side always, the means that input side means the input junction, whereas the two junctions. So this is one junction. So how already we discussed that the BJT contain the two junctions. One is between emitter and the base, another one is base and the collector. If you observe this either PNP transistor or NPN transistor, so this is the one junction, the junction between, so which terminals here, emitter and base. Again, you can observe NPN transistor also, the junction is formed between emitter and base. That is the reason. Whatever the transistor, either the PNP transistor or NPN transistor, one junction is always formed between emitter and your base. So here also same. Similarly, another junction is formed between collector and a base. So here also you can observe in NPN transistor. Another junction is a form between collector and your base here. That is the reason. Whatever the transistor in a BJT, it forms the two junctions. One is between emitter and a base. One is base and a collector. So by using these two junctions, we need to satisfy the transistor definition. Means that it transfers the low resistance device to a high resistance device. Means if we consider this is the input side, emitter base junction, we need to define that input side is low resistance circuit. If we consider the collector base junction is output side, we need to define the collector base junction is output resistance circuit. So based on that, then only it satisfies the transistor definition here. Now based on this, here I am showing the symbolic representation of NPN transistor as well as the PNP transistor here. And this is NPN transistor symbolic representation. It contains, we know that the BJT contains three terminals. One is emitter, base and a collector. So here also emitter, base and a collector. The difference is how we are going to differentiate which one is the NPN transistor and which one is the PNP transistor. That differentiation is done through this arrow mark representation for emitter. So here this arrow mark indicates that the flow of current the flow of current direction in a transistor. So here in an NPN transistor, the current flowing towards outside here. And here in a PNP transistor, the current flowing towards inside of the transistor here. So this is the symbolic representations of NPN as well as your PNP transistor. Now, based on that, so up to this point, we identified that the transistor contain the two junctions. One is emitter base junction, another one is your collector base junction here. So initially, I said that the transistor majorly used in some of the applications like amplifier, some switch and your oscillators here. So how you're going to make how this transistor or a BJT is acts as a switch or it is acts as your amplifier. So that is the reason. That can be defined through some modes of operation here. Either whatever the transistor, either NPN transistor or a PNP transistor here. But based on the junctions, we identified it contains two junctions here. So how we are forming these two junctions or how we are biasing these two junctions with respect to these two junctions or biasing, it defines some application of your transistor. Hence, here I am going to define these modes of operation here. So here I consider the two junctions. One is emitter base junction, another one is collector base junction, and this is the mode of operation. And we know that the biasing means so the way of approaching the external force to any junction, PN junction. So here also we are going to apply some biasing. The biasing in terms of either forward bias or your reverse bias. If you are altering these biasing conditions, the operation of the BJT is also changes. Based on that operation, with respect to your biasing, we define some mode of operations here. So we define the four modes of operation. Let us consider the first one is if both the junctions, your emitter base junction and the collector base junction, or both are reverse bias, that mode of operation is defined with the cutoff. If both the junctions are forward bias, again, how we can make this forward and the reverse means for an PN junction, this is the P-type material and N-type. If the P is connected to positive pole of the battery and N is connected to negative pole of the battery, then we can say that the biasing is forward bias. Suppose for an same PN junction, if the P is connected to negative pole of the battery and N is connected to positive pole of the battery, then this biasing is called as your reverse bias. So means here we are utilizing these biasing concepts or means we are approaching this biasing here. With respect to this biasing, we define some mode of operation here. So hence, if both the junctions are forward bias, and that mode of operation is defined as your saturation here. Then again, if the emitted base junction is a forward bias and the collected base junction is a reverse bias, and this mode of operation is called as active mode here. And if suppose if the emitted base junction is a reverse bias, if the collected base junction is a forward bias, and that mode of operation is called as reverse active. Now here, based on these modes of operation, if you want to utilize the transistor is accelerated switch, we need to use these two modes. Under this cutoff and the saturation, the transistor is acts as a switch. And the most of the major application of the transistor is amplifier. If you want to define the transistor is acts as an amplifier, we need to use this active mode of operation. In this active mode of configuration, the transistor is acts as amplifier A. So you remember this one. These are the modes of different modes of operation here with respect to your biasing conditions here. So now we'll see this, the operation of NPN transistor here. So here I consider this NPN, and this is the N-type material, P-type material, and N-type. And we know this means this is the formation, and this is N-type and P-type, and so this the formation of the two materials at one point, that is called as a base, ends, and this material is the base. And here I consider one end is represented with the emitter, one end is represented with the collector. Now we need to satisfy the transistor definition. So what is the transistor definition here? It transfers a low resistance circuit to the high resistance circuit here. Means this is based on the circuit, and this junction here, this emitted base junction is acts as the input side, and this is the collector, and this is the base. This collector base junction is acts as your output side. Means the input side we need to make a low resistance circuit, and this output side we need to make high resistance circuit. And how we are going to make the input is low resistance circuit and output side is high resistance circuit here. For this case, let us take, if you are taking the PN junction. So why? Because based on this construction, we are on the two PN junctions here. One PN junction is formed as emitter and the base junction. One PN junction is formed as collector and your base junction. So hence, whenever if the PN junction is a forward bias, then what happens, your diode is acts as a conducting, hence it offers very small forward resistance here. Suppose if a PN junction diode is under reverse bias, so what happens here, if the PN junction diode is under reverse bias, it offers very large resistance. That is the reason. Now we need to make the input side, we need to make forward bias, and output side we need to make reverse bias. Whenever we make this input side is a forward bias, it offers very small resistance. Whenever the output side, if we make the reverse bias, it offers the very large resistance. That is the reason it transfers the signals from low resistance circuit to the high resistance circuit. So how we are going to make this low resistance? Now we need to make forward bias. Hence, so here the base is we take in the P-type material. So hence the P is connected to positive pole of the battery, and the N side, this emitter side, the material is the N. Hence this N type is connected to negative pole of the battery. So in this emitter base junction, base is the P type. Hence the P is connected to positive pole of the battery. Emitter is the N type, hence N type material is connected to negative pole of the battery. Then with respect to this biasing, this input side, it acts as your forward bias, hence it offers a very low resistance across the input side. Similarly, we need to make the output side, we need to satisfy the reverse bias condition. Now, what is the output side here? Output side is formed with a collector and your base junction here. So here again, the base is a P type. Now we need to make reverse bias. So hence, P is connected to negative pole of the battery, and the collector side, the material is the ends here. So N is connected to positive ends. So due to this biasing, whenever the N-type material is connected to positive pole of the battery and the P-type material is connected to negative pole of the battery, then we can say that that particular junction is acts as your reverse biasing. Hence, now output side, with respect to this biasing, we made this output as a reverse bias. If this output junction is a reverse bias, we know that it offers very large reverse resistance. So that is the reason I made this type of the biasing at the input side and I made this type of the biasing at the output side. With respect to this biasing, I define the input side, I define the low resistance input circuit, and output side, I define the high resistance circuit. Then the signal is transferred from the low resistance input circuit to the high resistance output circuit. So this is the most important while defining the biasing condition in a transistor. Now with respect to this biasing, now what happens here, the emitter is, so here it is a emitter is contains N-type material. Here the majority charge carriers are electrons. Hence, with respect to this biasing, so N means the majority charge carriers are electrons and the electron has a negative charge particle. For this negative charge particle, we approaching the negative energy, then what happens here, it repels the charge carriers towards the another region here. So whenever the biasing is increases, the more number of the charge carriers are repelling towards your another region here. So hence, the majority charge carriers are diffusing from this emitter to the collector through the base here. So that is the reason I represented this a charge carrier flow direction towards the base, from this base to your collector here. And we know that, so the charge carrier, the electron is traveling like this and the current flow direction is opposite. That is the reason. Here, in this case, the electrons are diffusing towards the base, hence the current is flowing towards opposite direction and the current flow direction I represented like this. And in this case, whenever the charge carriers are emitted from this emitter and those charge carriers are traveling towards the collector through the base. And in this case, and we define the base is a very lightly doped and the region of the base is again very thin. Hence, only the sum of the charge carriers are constituted with the base terminal to produce the current. That current is called as your base current. And most of the remaining charge carriers are diffusing or attracting towards this collector and is a pairing with this collector charge carriers. Hence, it produces a current and that current is called as your collector current here. And here, from this operation, we define that here, emitter is, the most point is, always the emitter is, M is the charge carrier. So hence, the maximum current depends upon your how much charge carriers are emitting from the emitter, hence I. And this emitter charge carriers are pairing with some base as well as a collector, hence the total emitter current depends upon the base current and your collector current. So from the representation, I is represented as the summation of base current and your collector current here. And in this case, and based on the construction and based on the doping levels and based on the regions of the BJT, only the 5% of the charge carriers are constituted with a base. Remaining 95% of the charge carriers are constituted with a collector to produce the collector current here. So this is the principal operation of a transistor here. So up to this point, in this session, we discussed what is the BJT and symbolic representation of the BJT, how to form the BJT and operation of your BJT. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.